Okay, welcome back. We're going to finish up these function slides today and make sure that I'm actually recording. Yes, let us continue where we left off. So functions are nice because they let us encapsulate a bunch of operations into a very small little thing. Okay, a nice package that we can keep on calling as much as we want. So we stopped here on const parameters. Are you ready? So let us begin with those. And so let me try and motivate the problem. We like using references. They're nice in function parameters. Like if you pass along, like you make an inc function that takes an int reference. It's a void function, and it just does I++. That's beautiful. References do that for us. Oh man, that's nice. They can update an original value from another function. But sometimes we would like to use the memory savings. We'd like to save a bunch of stuff, like maybe we have a large vector instead. Vector of int reference, for example. Maybe we have a giant vector that we want to pass to a function instead, and we'll use references to save all that memory, but we don't actually want to modify the stuff. We just want to make our programs run faster because we've saved memory so that things don't get copied. Is there a way to make it so that you can use references but also keep yourself from modifying what gets passed to you? And the answer is yes, and it involves the keyword const. Okay, so constants, that's what const is short for, you can assign to, and then those things can't change, right? So let me show you those. Dun dun dun. So vim const.cbp, why not? So if I have a const double pi, I can't change it. That's a compiler error, right? So it's going to show me cannot assign to variable pi with const qualified type. It's just something I can use and I can never change it. Okay? So that's const. It's like a qualifier in front of a type. It modifies the fact that you have a double, but also you have a double that you cannot change. Okay? So that's pi. But you can do the same thing because what are variables, what are function parameters other than just variables? It's just a normal variable, right? You can use const in functions, okay? You can take const parameters, okay? That is the idea here, const parameters. And those functions that take const parameters cannot change the value that gets passed to them. They cannot change that constant variable. Okay, so that's wonderful when combined with references. That makes it so that you cannot change the reference variable, but you get all the memory savings of using references. Okay, so I encourage you to use const references as much as humanly possible in your programs. So here's my example of a function that takes a const reference. Let's make a sum vector function. Okay, dun dun dun. Okay, so what it's going to do is it's going to give back the sum of all the elements in a vector v. Vector of ints, v. And we're going to take that vector by reference, first of all. And let me show you what we can do. We can say, well, I'm going to need to include vector. We can say, okay, the sum is int sum equals 0 for int I equals 0, I is less than v.size, I++, sum plus equals v at I. This is all well and good, return sum. So this gives back the sum of all the elements in the vector v. So if it was v equals 1, 2, 3, for example, we could see out the sum of v, and we get 6 back, right? So let's confirm that. Const.cpp-o const. Bam. Yeah, so we get 6. Wonderful, wonderful, wonderful. But the issue with references, we could totally do this. If v isn't const, we can do this line right here. We can say v at 0 equals 42. We can update that vector. Oh no, because now the sum won't be the same. Yeah, we get 47 now. That's a bad thing. We don't like that. We don't like to be able to do that. So you can say const instead to force yourself to not be able to change anything. Okay, you are stuck with the vector v as it was passed to you. Okay, you're not making a copy in the call, but you're forced with the original values. Okay, so now this is not even going to compile. It's as if I was changing something that was const. Okay, so assignment of read-only location. Wonderful. That's exactly what we want here. Okay, so this is not allowed. It's a compiler error when v is const, and that's quite nice. It keeps us from making silly mistakes and changing things that we probably shouldn't be changing. Okay, that's const. Quite nice. I hope that you see the use of it, at least. And yeah, use const references as much as possible to save that memory and also keep yourself from modifying things. Okay, so now here is a topic that is something that I want to warm you up to. It's going to be a huge, huge issue when you take CSCI 41, but we're not there yet, of course. So I'm not going to test you on this. This is a 41 topic. We hit it really hard there, but it's something that I want you to start thinking about from now on. Okay, slowly but surely, we're going to get you to think about the complexity of your program. How fancy is it? What does that even mean? Okay, so there are some ways that you can time your program. You can totally count the number of seconds that it takes to execute your program with like ctime. You can use this library here at ctime.h. You can get like the current time with the clock function and like figure out when you call clock again, you can subtract and figure out how many seconds it took to execute the program that way. But every processor is different. The one on your laptop is different from the one on your desktop, is different from the one on your phone. Yeah, they all run at different clock speeds. Like you've heard of, like, this is a 2.4 gigahertz laptop. Things like that. So how do you account for this when we're trying to talk about complexity of programs, how fast something is? There's a better way. There's a better way that doesn't involve how fast your computer's processor is. There's an idea of how fast an algorithm is. Okay, so some programs are still faster than others, no matter what a processor speed we have. Okay, so no matter which processor you're using, some things are always faster than others, and I want to teach it this way. So there's an idea of basic operations inside of every program, and those we can think of as taking one step of execution. Okay, so every time we do something like int x equals y times 2 plus z, this is going to take a few steps. Okay, all of these little arithmetic operations, those take a step. Assignments of variables to values take a step. Printing takes a step, we say. So this particular example has a multiplication. We got to do that first to y, and then add the result to z, and then put all of that into x. So that's 3 steps total. Okay? That's the idea. And so this is a kind of number that is independent of the speed of a processor. I hope you see that. Okay? So yeah, just keep track of these basic operations, and now we can see how fancy our programs are, how fast they take. There are some very non-basic operations now, and those are ones that involve repetition. Okay, summing a vector, for example, takes a different amount of time because some vectors are huge and some are small. So you have to like split it up. You have to like multiply the work for one iteration of the loop by how many steps are in the body of the loop, for example. Calling a function also takes a number of steps because all of the body of the function takes some time. Have to consider the body. And for example, also like reading a bunch of ints until the user types -1. You have no clue when they're going to type -1. They could type anything but -1 for a million years, and then they'll type -1. Okay? There's a different way to explain these things. Okay? So yeah, pretty much every single line statement you can think of that doesn't do anything fancy is more or less basic. And technically you can count this as just one step. Okay, so that's where I want to leave us here. But we can do cool things with that. We can come up with a number for every program we write to say how fast it is. Okay, step 1 is we count all our basic operations, and then step 2 is we write a formula in terms of a variable input size. That's the key. Usually it's called n. Like if we have n numbers in our vector, it'll take n times whatever the loop body's time. Okay, loop body steps to like print it out, for example. Okay, so you get to multiply it by the size of your input, and here is a little idea of how fast things are. Okay, how fast programs are relatively, and we have numbers based on that. How fast is it to add 2 ints? Well, that's just one basic operation. We call that constant time. So if you hear that in your book or in 41, you're going to eventually learn it. Now you know. Now you have a head start. To sum n numbers, well, it's going to take n times the amount of time you're spending in your loop that's summing. Maybe you're printing out some extra stuff. Maybe you're just adding and then putting into a variable. That's at least 2 basic operations. So it's some constant times n, and we call that linear time. And then we have fancier programs. So that's constant time is faster than linear time is faster than polynomial time, we say. And this is like n to some power. N by n boxes is a good example of polynomial time, because not only, like if you want to print a 4x4 box, not only do you have to print 4 stars on one line, you have to do that whole thing 4 times. So that multiplies it. So you suddenly have to do, if n equals 4, you have to do some constant times n work, right? That's the total number of stars, and then you have to see out that, and update your loop variables, a lot of little basic operations, and then it becomes polynomial time. Okay, I just want you to start thinking about this. It's nothing I'm going to test you on, of course, but you might hear about it a little bit in your book, and now you've at least seen it once. Okay, that's all. So with that, let us move on now to algorithms. So algorithms are all about commands plus state. Okay, so we want to be able to do a bunch of things to the state of memory. Like maybe we have a bunch of little variables and they need to change in a very certain way using a bunch of different programming commands to like maneuver data around, move it all back and forth to get the right number that we want, which is our answer. Okay, so let's talk about at a high level how to design an algorithm. Okay, that's important. So here is the idea. There's a bunch of different architectures. There's a bunch of different little patterns for designing programs, and everybody has their own idea of how this should be. Okay, everybody has their own opinion, and I'm going to teach you a very simple one. Okay, so I guess the question I'm trying to answer here is there like a method for building good programs, for building beautiful programs, for building programs that are likely to be correct? And the answer is yes. There is one way. There's multiple different patterns to use when you're programming something and making an algorithm. I'm going to show you one, okay? And this one thing is called a state machine, all right? And a state machine, what it does is it abstracts a process away, all right? So let's talk about that. The idea is you have a bunch of little states, all these circles, all of these little rounded rectangles. Those are your states, okay? And you can transition in between states by some action. All right, so let's talk about this one. So this is like maybe you start out at home, and or no, let's say you start out in bed, like the day is beginning. That's where you start. That's your start state, and you wake up. So you transition to the home state. So you're sitting at home, but you're awake now. Okay, so now you're in this state, and then it's time to go to work. So you're going to take the train to work. Apparently, we live in a nice large city with trains, and then we end up in the work state. You see that? We follow these two transitions to change our state, and then work is over with, so we're going to take the train back home, and then we end in the home state. Then we have dinner, browse Reddit, and it's time for bed, and so we need to followed the sleep transition to get back into the bed state, and then the whole process starts over again. And maybe the next day is a weekend, so you wake up and then you go straight back to sleep. You don't go to work. So you can follow all of these different transitions as you would like. Okay, so there's a concept of transitions, moving between states. Okay, so that's a simple example. Let's go down to this one, because the idea is if you can separate your program into different states and transitions between them, life becomes very easy for you as a programmer. Okay, this is our goal with state machines, for me to teach you a nice way to make programs work so that you don't ever get lost in all the details. Here is an example of maybe making a program that handles like Uber or Lyft drivers. And so you start out here and you request a trip as the user. So now you're sitting, or like the Lyft or Uber app is sitting in this state, the trip requested state. And then it needs to run your credit card to make sure you're trying to actually pay for this trip. And hopefully it goes through. If it doesn't go through, it's going to ask you to supply another credit card, right? And the driver is not going to be assigned just yet. But if the credit card does go through, then you're in the driver assigned state. And the driver can come pick you up and take you somewhere. And eventually you'll get to your destination, your trip is complete, and the driver goes back to being unassigned. They can also go there from if the customer cancels, apparently. And yeah, that's what ends the trip. That is how your program can maneuver through its different states. And the idea is it keeps you as the programmer honest, right? So if you're in this state, because of the way the transitions work, you're never going to try and hit the credit card of the customer ever again. Okay, that's impossible given your transitions. That's the beauty of state machines. They make it so that everything your program could possibly do is spelled out. Okay? State machines spell out exactly the kinds of operations that your program can perform. I'll say ops. Your program can perform. Okay, and that's a beautiful thing because it makes things easier for us as the programmers. Okay, so if you have an algorithm, a problem that you want to solve with an algorithm, you can come up with a state machine for it sometimes by grouping your program into different states and actions that take you between those states. So here's another example. If you're a student, I'm going to pretend that you are implemented as a two-state machine program. Okay, you have a learn state and you have a practice state. So here's my state machine of you down here. And the idea is you start, that's what this arrow means, you start in the learn state because that's the first day of class, you're ready to learn, right? And the lecture keeps going on and on and on, so you stay in the learn state as long as the lecture isn't finished. And then the lecture's over and I assign a lab. And then it's time for you to practice, right? As long as it's not finished and I haven't posted a new lecture, you keep practicing, and your lecture maybe gets posted for the next day, then it's back to the learn state for you. And you keep on maneuvering around and around and around, and this is maybe how I think of you as the student, right? And there's another concept of a final state, and we'll get to that in a second. So just to say all this in written words, you keep on alternating between states, following the transitions, and you stay in the same state as long as you're not done. And the arrow signifies an initial state. That was your first state. You are ready to learn. And then your final state, it's a state with little 2 circles in it. That's where you end up. That's like, okay, you're done now. I accept the program. It's finished. Okay? So your final state will be practice because you'll take the final and then leave. There will be no more lectures. Okay? That's the idea. So that is a state machine. It's actually called a finite state machine because there's not an infinite number of states, but you can also have infinite state machines just as easily. So my example for you of a state machine is counting words. So I'm excited for this. So let's count the words in a string with a state machine. Okay, so this is the secret. It's going to be wonderful. We're going to do this. We're going to read all the characters in a string one by one. So we're going to get something from the user. We're going to get a line from the user this time, and we're going to keep track of the white space that we see. So if the user types in a string, like this is our line that we get from the user, hello world, blah, 42 exclamation point, like that's our string, then how do you think we'll go about counting the number of words in this? Because we have a word here, we have a word here, we have a word here, and we have a word here. If you think hard enough about it, the answer is going to be white space. So every time we see a space character, that's going to bring us to a new word. You see that? Every time, like a certain number of spaces, even if there's multiple, that breaks the word that it's between. Okay, that's the idea. So yeah, this is the key idea. White space separates words. Every character is part of one word, part of an old word. Every non-space character, I should say. It's part of an old word or the start of a new one, I should say. Sorry, start of a new one, and maybe this should be existing. Who knows what I was thinking when I was writing this. Okay, that is the idea, and let me show you this. So let's just start making the state machine maybe. Let's put the example over here. So initially, we're going to have two states. We're either inside a word or outside a word. And we start out outside a word. Okay, that's where we begin. And we also keep track of a count. Okay, there's a count sitting here. And this is the state machine that counts words. Are you ready? So you're going to go one character at a time. You're going to read the first character. It's an H. I want this that I can use. Yeah, so you're going to read the first character. It's an H. And then you're going to keep going. It's the first character. It's non-space, so we're now inside of a word. Whenever we read a non-space character. And then we're sitting inside a word. And every time we're inside a word, darn it, just keeps putting them all together, doesn't it? Every time we're inside a word and we see a new character, we see E-L-L-O, that's not a space, we're still inside the same word, okay? Non-space. And now let's finish it off. So the second you see a space character, you're now outside a word again, aren't you? Oops, keeps doing that. Sorry. So now you're outside a word, and you followed a space transition to get there. And we're going to talk about count in just a second. And every time you see a space, you're still outside a word, right? So maybe there's two spaces here. 1, 2. You're still outside a word as long as you see a space. So this is the state machine. And now it's very easy to attach counts to this as well, because the idea is every time we transition to inside a word, that state, there's a new word that we found. So initially, we've seen nothing. We're starting here. The second we see a non-space character, we should add 1 to our count. You see that? That's the beauty of it. So we see the H, we add 1 to our count. Bam, it was at 0, now it's 1. And now we keep seeing characters that are part of the same word. They're non-space characters, so we stay inside the word state. Then we see spaces, and now we're outside a word. We're ready to see another one soon. And we stay there as long as we see space characters. Okay, I hope you see that. And the second we see a new word, we follow this transition. That's the only one we can take, and we add 1 to our count. Isn't that beautiful? And then we'll stay inside a word, another space. Ooh, now we're outside a word. Hopefully we're going to see another one. These are 2 space characters, right? And oh, we see another character, so it's another word. Now we're sitting here again. You see that? So we keep on saying inside a word, outside a word, outside a word, inside a word again. That's the fourth word. Oh man. And then we'll hit the end of the input, and that's where we stop. And we counted the number of words that way. Isn't that fun? So that is how you count words with a state machine. And now I want to code it up for you. All right, so let's do it. Let's make a folder for this, because it's eventually going to turn into a library. So let's make dir, what do we want to call it? Count words. Yeah, so there it is. Let's cd into it. And of course there's nothing there to begin with. Let us make something there now. Count words. There we go. And let's make a file called, I don't know, we're eventually going to need main.cbp, right? So let's make a file with a main function at least. And the idea is we're going to get something from the user. We're going to get a string from the user. So I'll make string line, and then we'll say get line with cin, and then the string that we want to read into, which is line. Okay. So we do that, and then now we have the line that the user typed, okay? And then we're going to count the words on that line, okay? Maybe we'll say count words of the line, and maybe we'll see out the number of words in that line. So that's the kind of function that we want to have. Okay, so let's see here. We're going to need to make this function. I wonder if we also want to test it. Maybe if there's time. So the function is going to look something like this. We have, let's see here. We have int, because we're going to give back a number. That's the number of words we see. Count words. And then we're going to take a string, s. Whatever string it is, we're going to count the words in the string. Okay, we're eventually going to move this to its own file. We're making a library for ourselves, right? So, also, let's use constant references for this, so that we don't copy strings around. Hey. And now we're going to have to worry about states. Okay, so we start out in the outside a word state. And it's customary to make these very capital, all caps. So our starting state is outside a word, and then we're going to read every character and potentially transition. So let's read every character in the string s. And so I could use the fancy for loop if we wanted to. You could say for char c in s, or you could do it the fancy or the less fancy way. You can say int I equals 0, I is less than s dot length or s dot size, I plus plus. Either way works. And so now for each character, read the character and follow the transitions. So we're going to have to figure out if the character we just read, so we're starting here, was a non-space character or a space character, because that's going to tell us what kind of transition we should follow. So maybe we should just get out the character. Char c, the character that we just read, is it's s dot at I. You see that? It's the ith character in s. That's our c. That's our current character. Let's just call it char, current char. How about that? And now we have to see if it was a space or not, because that's going to be how we follow our transitions. So let's see here. And also, our transitions are going to be different depending on which state we're currently in. So let's do this. If state equals outside, we're going to do one thing. Else, that means our state was inside, right? Those are the two possibilities. We're going to do something else. So when we're outside a word, when we're in this state, we stay if we saw a space. We leave if we saw a non-space. So stay if space, leave if non-space. So if current char is a space character, oops, is space, you remember that from CC type? We can use that now. If it's a space, our current character, we're going to stay. So state stays outside. We don't really even need this line. Otherwise, it was a non-space character. We need to transition. Because our state is outside, we just saw a non-space character, we need to transition to inside. You see that? So state is now inside, and also we need to add to our count. So that's another thing we need to remember to always do. Int count starts at 0. That's the count of all the words we see. We'll eventually increment that and return it back. Okay, so that's that. Let's remember to do that, and then we'll work on the other case. If we were in the inside state, we stay if we see a non-space, and we leave if we see a space. So stay if non-space, leave if space. So similarly, if we see a space for our current character, we are going to, this time, we're going to leave. Our new state becomes outside. You see that? We're following this transition from inside to outside when we see a space. And then otherwise, oops, no, it's not going to let me do it, is it? Dun dun dun. I forget how to disable this. I'll have to figure it out, that's for sure. I can always do that, I guess. So that's that state. Else, we saw a non-space character, if we're in the else case. So we stay. So our state stays inside. And we don't, oops. We don't change our count or anything when we transition from here to anywhere. Both of our transitions don't increase count. It's only when you're going from outside to inside. Okay, so that's the idea. That's our program. And all we have to do in this function is remember to return this count that we're building up. Yeah? So return count. And there we go. So now this should work, in theory. Let's try it. So the number of words in whatever the user gave us is going to be the result of calling this function, counting all the words using our state machine, and returning back the final answer way down here. Okay? So let's see if it works. Dun dun dun. This is main.cbp-o main, and we're eventually going to turn this into a library, remember. But now we're being lazy. We'll fix it later. So we need to get a word now. Or, sorry, we need to input a line. So, I don't know, what's that sentence that has every letter of the alphabet? The quick brown fox jumps over the lazy dog. Enter. So the number of words is apparently 9. And so it's going to follow these transitions. It's going to start outside, transition from outside to inside, increasing the count when that happens, And so it's telling us that it sees 9 words. 1, 2, 3, 4, 5, 6, 7, 8, 9. Heck yes. Yes, it did see 9 words. And it's not going to get tripped up if there's extra spaces. So for example, if I did this instead, and I added, oops, can I go backwards? No, I cannot. Never mind. Delete. Jumps over tab, the, lazy, space, 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 dog, tab, tab, space, space. There's no difference. Still 9. You see that? So it just stays in that same state, using just following the transition that keeps it in the outside a word state when it sees multiple space characters, just like it stays inside a word when it sees extra characters. So it doesn't matter. As long as it's seen 1, it knows where it is. So hopefully that was fun. That was counting words using a state machine. Now let us transition this, no pun intended, to a library. So we want to split these up. The main function should call the library function, but we should make those .h files and the .cpp files. Okay, so the first file, let's call it, I'm going to make a new file called countwords.cpp. Yeah? So that is going to include the implementation of this function. Bam. Paste. And also it's customary to include the header file. So include countwords.h, and also using namespace standard because we're going to be using strings. Okay, so let's see here. Now we need the .h file, and it's really unhappy because it doesn't know what a string is yet. We have to include that library eventually. Let's see here. Yeah, let's go straight to it. Let's edit the file called countwords.h, and remember to use the header file guards. So if not define, define, and if, that makes it so that we don't infinitely include ourselves. And then back here in main, let's save this. Then back here in main, we can include that file. That's how it knows about it. Include countwords.h, and that'll tell it about the countwords function the second we put it there. We have to first declare the fact that it exists, so put it there. And we'll also include the string library because this needs strings. Notice that I'm putting the string library right here, and then we get it for free here because it's being copied and pasted. Now, one thing that you're never supposed to do is use namespace standard in a header file. I might talk about this later, but I'm going to say it once right now. The reason why is because the second you say using namespace standard in your header file, it's going to get copied and pasted wherever you include it, right? Any file that didn't want to use the namespace standard now is forced to use it. That's the idea, because it's being copied and pasted for us. So it's a good idea to never use it and just say standard : all over the place. So for now, we're just going to do it that way. And now it should be happy. So countwords.h exists. It is implementing all the stuff here. If I try and change this and reload it, it should be slightly happier. Maybe not. Let's open it up again. Now it's happy. Okay. Yeah, just need to be reloaded. Now it knows about strings, and we don't have to use standard because we can use namespace standard in the .cpp file in the implementation file because that's just for us. Okay, and then main is including countwords.h, so it knows about the countwords function, and now it's going to be all happy. So again, I'm going to have to reload this so that my editor knows what's going on, but that is the idea. So that is our big happy family of a library and our main file that includes the library and uses it. So remember the way to compile this is we say, let's see here, we say G++ standard equals C++17 main.cpp, and then we also give countwords.cpp. So remember to give every implementation file when compiling. So it's like that. And then you can call it whatever you want. So we'll just call it main. Okay, and that is all you need to get it compiling. You put that all there. Give your 2 files that you want to use. in the compilation process, and then the main file gets made for you. And you can run it, and bam, it works. Okay, number of words is 2, and it even should work if we gave nothing. The number of words is 0. See that? So that's not bad at all. So, yeah, I think that's everything that I wanted to talk about there. That is counting words using a state machine. It's wonderful. Hopefully it's making some sense, and we made a nice library about it. Maybe just for fun, let's make a test too. Hey, let's make one test. Maybe a couple, why not? Just to give us some practice. So this is good practice for your lab as well. So let's make the assert true function instead. Let's do that down here. And instead of using all of this, we will comment that out, and we'll actually run our tests instead. So test 1, test 2, test 3, for example. Let's make 3 tests. And then we'll implement them, and they'll use the assert true function that we have now. It's going to be void assert true. You make sure that a boolean ends up being true, and it has a description. So if b is true, we pass the test. Otherwise, we failed it. And let's make 3 tests for ourselves. So the first one can maybe be the empty one. Let's see here. We can assert true, ensure that our function works, count words of the empty string. That should be 0 words, right? So, oh, sorry. I want to say it like this. Make sure that the count words of the empty string is 0, and the description could be empty string. So we're making sure that it gives back 0 when we call count words. You see that? That's what we're doing on an empty string. So that can be the first one. Then, let's see. Let's try another one. Actually, it might have done me better to just copy that thing. Test 2. Count words in hi mom with some spaces and let's see, and a tab, 2 tabs and a space. That should still be 2. So we can call that hi mom, or like 2 words, and then we have our 9 words example. We said that that was 9, right? So, and this can be test 3. So these are 3 different tests that make sure we're doing the right thing. The count words of the empty string is 0, the count words of a 2-word string is 2, and count words of a 9-word string is 9. And we should give it another description. I don't know. Let's call it the quick brown fox. Dot, dot, dot. How about that? Okay, so let's try this now. That's a nice test, I think, and we passed them all. Beautiful. We check that what we get back is what we expected. What we get back from this function call is what we expected. Yeah, that's the idea. So I think with that, that's where I want to leave us. So some exercises that are a good example for you, I hope, is to write some tests, maybe for the counter library that we made from the past lecture. So you can steal this assert true function, you can follow these patterns, but make a bunch of calls like this. Be like, let's make sure that after we init the counter and ink it 3 times and decrement it and get count, that should return 2 back to us. So if we do all those things in that order, we should assert true that get count finally at the end of all those things. So like init counter inc, etc. After the end of all of those, get count one last time, assert that that gives back 2. And you give a nice description. That is a nice test, I think. So that's one good example. I think you can make up more as well. Okay, so that would be helpful and fun. Now, another nice thing, a very cool thing, is to use multiple libraries at once. Use our counter library to implement word counting. Yeah, you can include one library inside the other, and then you compile it with your 3 CPP files this time, because you have to include the counter library, or maybe I should just write it here. You need the counter library, you need the count words library, and then you need your main function file. Those are the 3 CPP files you need to use to compile that. So that would be a fun exercise as well, I think. Just bringing it all together, bringing it all home. And then a very good example, if you can do it as many times as you like, is to take a previous lab, or a xylab, which is a word, and turn those into functions. So like, what are the types involved? What should they return? Take some of your very long main functions and translate them into function calls. Okay, so that I think would be helpful as well, to just get everything settled in your mind. But I think that is all I have for you today. So that is the end of our function slides. You are all professionals now at functions, and we're going to come back in the next lecture and talk about classes and structs, and it's going to be really, really cool. We have data and functions at the same time, so it's really fun and exciting, and I'm excited to teach it to you. So yeah, with all of that, I will see you in the next lecture.